My name is Richard Pexa, and today I will be talking about VFD De-rating and understanding how environment affects the performance of a drive. So I'll give you a little background about myself. I've been with ABB now a little over a year as a sales application engineer in the HVAC department. Other HVAC experience, though, I bring to the table is that I work for Greenheck Fan in a variety of different roles, and I was with the company for about 4 years. I received my education from Marquette University and received a degree in mechanical engineering. So let's talk about our agenda and what we're going to cover today. First, we're going to define what derating is, and then get into why you actually want to derate a drive. There are 4 main topics of derating we're going to cover today, and they are altitude, temperature, carrier frequency, and input voltage. And as the slideshow goes on, we'll go into all these in more depth. So VFD derating, how do we define it? So derating is defined as determining the new maximum output current rating of a drive that's less than its nameplate due to environmental conditions, operating setup, and/or the input power source. So when we're talking environmental conditions, we're going to be talking about the ambient air temperature in which that drive is installed in, and then also what altitude is that drive going to be installed at. When we're talking operating setup, we're going to be talking about, it's a feature inside the drive of what the output carrier frequency is of that drive, and we'll go into that a little later. And wrapping it up, when we talk about input power connections, we're talking about, are we going to be only bringing single-phase input voltage to this drive? Or are we going to be supplying this drive's power off an open delta supply transformer? So remember though, when we're talking about drives and sizing drives, we can't just size the drive off the horsepower of the motor we're applying the drive to. We need to size the drive off the amperage and the horsepower of that motor. The end goal though, when we're looking at derate, is that we're going to determine if the drive is sized correctly, or if a larger size drive or larger size horsepower may be required. So why do we want to derate a drive? Well, VFDs produce heat. The things that produce heat on the drive are the input diodes and the IGBTs or transistors on the output. If you look at how a drive is actually built up though, you'll see that almost half the weight, if not more, is the aluminum heatsink on the back. And that aluminum heatsink helps dissipate all the heat that's generated from those input diodes and output IGBTs. There are factors, though, such as altitude and ambient temperature, that can limit the ability of the drive to remove heat from its heatsink. Another factor on how the drive produces heat is that carrier frequency, which relates to the output of the drive. That carrier frequency can also increase to the drive's heat production. When we're looking at derating though, the main also goal is that we want to protect all those electronic components from overheating and failure. So let's get into altitude. There are 2 main concerns when we're talking about derating for high altitude. The first one is cooling, which is our most common, and also the other concern is electrical component spacing, and the spacing is there the electrical component spacing is there to prevent arcing on internal components. So let's talk about cooling first. At high altitudes, a drive has a lower cooling efficiency due to the air being less dense, and that less dense air passing over the heatsink can't remove as much heat like at a lower altitude can. All drives are rated out of the box for 3,300 feet above sea level, and there's no derating required. Once we go above 3,300 feet and all the way up to 13,200 feet, there's a 1% reduction of the drive's output current and power, which occurs for every 330 foot increase in altitude. I just kind of want to put this in perspective though, because as being located in Wisconsin, I don't think about altitude too much. But I kind of wanted to bring up this topographic map of the United States. And if we look at this map, we'll see that the greens are at our low end And as we go to the tallest points of the United States, those are highlighted in white. If you can kind of zoom in on the graphic and kind of squint at it, you'll see that once we go from, I would say, in a yellowish to start getting into orange, that's when we go past that 1,000-meter mark, or 3,300 feet. And if you're selling drives into anywhere that's located in these orange colors, most likely you're going to have to start possibly taking into account some sort of D-rate. Some major cities, though, you can see right off this map are like Albuquerque, Denver, Boise, Salt Lake City. So those are just some examples. So let's do an example, though, when we're talking about altitude. So our first example is that we have a drive that's going to be installed at 5,280 feet, and the drive we're using is a 10 horsepower, 480 volt three-phase rated drive that's rated at 14 amps. We're going to take that drive and connect it to a 10 horsepower, premium efficient, 460 volt motor that's rated at 12 amps FLA. So let's start doing some math here. We take our 5,280 feet and subtract it from 3,300 feet, and we get 1,980 feet. So we take our 1,980 feet and divide it by 330 feet, and we're going to see that we're going to get a 6% D-rate of the drive's maximum continuous output current. We take that 6% and we multiply it to that 14 amps of the drive, and we calculate out that we get about approximately 0.8 amps of D-rate. We subtract that 0.8 amps from 14, and now we see that we get 13.2 as our new value for our maximum output current due to the D-rate. So let's check. 13.2 amps is greater than 12 amps of the motor's FLA, so no upsizing of the drive is required. Let's do another example. So in our second example, we're going to take a drive that's going to be mounted at 10,000 feet above sea level. This drive is rated for 150 horsepower and at 180 amps. We're going to connect this drive to a 150 horsepower motor, and that motor's FLA is 170 amps. Let's do our math again. 10,000 minus 3,300 feet gives us 6,700 feet. Take that 6,700 feet and divide it by 330, and we're going to get a D-rate of approximately 20% D-rate of the drive's maximum continuous output current. Take that 20% and times it by that 180 amps, and we're going to get 36 amps of D-rate. Take that 36 and subtract it from 180 amps, and we get our new output rating, our new maximum output rating of the drive will be 144 amps, and this is all due to the D-rate. We do our check, and we're going to see that 144 amps is less than 170 amps. So we're going to have to upsize our drive. If we go to the next size drive up, it's going to be a 200 horsepower drive. And instead of going through the whole math again, we'll just do it real quick at the bottom. 200 horsepower drive is rated at 240 amps. So we do our check here. 240 amps minus our 20% of 240 gives us 192 amps of maximum output current D-rate, and that is larger than 170. So in this case, we did have to go up a drive size. So continuing with altitude here, I kind of want to bring some motors aspect into this presentation. So just as drives need to be D-rated for proper cooling at altitude, motors also need to be D-rated for altitude as well. Motors D-rate in generally the same way as drives do, but I always want to say check with your motor supplier for the exact details on how they handle their D-rating for altitude. This is going to become more clear on the next slide, but I want to bring this up now. Knowing if you're D-rating against a horsepower required to do the work at altitude or a motor horsepower that was already D-rated is key. And why I say it's key is if you're D-rating against an already D-rated motor that was increased in horsepower already, that's going to lead us to doing a D-rate of a D-rate. And when I talk about a D-rate of a D-rate, that can lead to a drastically oversized drive. And we're going to see this more clearly on our next example on the next slide. So in this example, we're going to be installing a drive on a supply fan at a certain altitude. When we look at the supply fan, the work required at design is that it's going to require 40 horsepower to move the air required. So let's add the motor to the fan, and by looking at this altitude that we're at, the motor is going to be derated to 50 horsepower for thermal reasons. Next, we're going to take that drive, we're going to put a drive on this fan, I should say. And when we look at the motor powering this fan, we see that it's 50 horsepower, and we're going to derate our drive then to 60 horsepower to maintain those cooling, to maintain the cooling of that drive. So let's look at this whole example now. We just put a 60 horsepower drive on a 40 horsepower load, when actually a 50 horsepower drive would have worked. Usually when we look at new construction jobs, you can see that on the schedule, the engineers will usually call out what the working horsepower is required to do that work. So that's usually you don't usually run into this derate of a derate on new construction. It's more in these retrofits is where we have to do our homework. When we're looking at retrofits, we want to make sure we're putting the right size drive on there and understand what the actual horsepower is of that working load at an altitude. As we wrap up with altitude here, I mentioned earlier that we get concerned about electrical component spacing. And when we worry about electrical component spacing, it's at really high altitudes, like above the 13,200 feet. The reason we worry about the component spacing is that the air density decreases so much that electrical arcing can actually occur more easily. And this arcing is a phenomenon known as Paschen's law. So now let's talk about temperature. So I mentioned this earlier that the VFDs produce heat from the diode, the input diodes, and the output transistors or the IGBTs. If we're going to install a VFD in an already hot environment, such as an unconditioned mechanical room, the drive may require upsize or derating to allow it to be able to dissipate the heat better. So the ACH 580 nameplate rating is valid for ambient air temperatures between 5 degrees Fahrenheit all the way up to 104 degrees Fahrenheit, or that's negative 15 degrees to 40 degrees Celsius. This 5 to 104 degree range applies to UL types or NEMA type 1 and 12 enclosures. The NEMA 3R enclosures can operate from 0 degrees Fahrenheit all the way up to 104 degrees Fahrenheit. If we are operating now in an ambient temperature of 104 to 122 degrees Fahrenheit, or 40 to 50 degrees C, you're going to need to derate the maximum output current of that drive by 1% for every 1.8 degrees Fahrenheit or above that 104 degrees. Or you can think of it as 1% for every 1 degree C above 40 degrees Celsius. So we have an example here. In our example, we're going to take a 10 horsepower drive that's rated at 14 amps, and we're going to have that drive operate in an environment that has the ambient temperature of 110 degrees Fahrenheit. We're attaching this drive, though, to a 10 horsepower premium efficient motor that has an FLA of 12 amps. So let's start doing our math. 110 degrees Fahrenheit minus 104 gives us 6 degrees Fahrenheit. Take that 6 degrees and divide it by 1.8, and we're going to see that we get a 3.33% derate of the drive's maximum continuous output current. Take that 14 amps, that's the drive rated amps, and we times it by 3.3%, and we get approximately half an amp. Take that 14, subtract it from that take that half amp, subtract it by 14, and we get 13.5 amps of maximum output current due to the derate. Let's do our check. 13.5 amps is greater than 12 amps, thus no upsizing of the drive is required. So when we get into applications where a UL type or NEMA type 4 or 4X package is going to be mounted inside or outside in an ambient air that's going to be above 104 degrees, the derating of the drive by 1% rule doesn't apply. because in these types of applications, we're using air conditioners to provide the cooling. Above this 104 degrees Fahrenheit, the air conditioner may actually be required to be oversized itself to deal with these higher than 104 degree temperatures. At this point, we can still provide a 4 or 4F solution, but it needs to turn into a custom product. And when we do a custom product for this application, we need to know the maximum air temperature so we can correctly size the air conditioner that's going to be on the side of that unit and maintain that drive's coolness inside its enclosure. So let's look at this kind of cool feature though. When we're looking at derating, we can actually combine temperature and altitude, and in some cases, we can actually avoid a derate. If we know that the ambient temperature is going to be below 104 degrees, or positive 40 degrees Celsius, the derating though can be reduced 1.5% for every 1.8 degrees Fahrenheit or 1 degree C. 1 degree C reduction in temperature. I want to note this, and I'm going to say it probably multiple times throughout this presentation, but you cannot use this analysis to get more current out of a drive than the maximum rating on that label. In the next slide, I want to show you guys a chart. On this chart that we're looking at now, this is actually a chart that's inside our manual for the ACH 580, and this will actually show how you can possibly use temperature and altitude, combine them together to your advantage to avoid a derate. As you can see, we have multiple curves on this line, or multiple curves on this graph, or more or less are just straight lines. You can see that we have a 1.0, which would be a no derate, 0.95 derate, 0.9, 0.85, and 0.8. And if you follow those lines, you can actually see at what temperature and at what altitude your drive is going to be operating at, how much of a derate do you need to do, or if you'll even need to do one at all. So you can see that at 40 degrees C, if we're not going to do a derate, at 40 degrees C, our maximum altitude can be 3,300 feet or 1,000 meters. If we go on the other side of the spectrum though, if we know this drive is going to be in a cool mechanical room that is only going to be at 20 degrees C or 68 degrees Fahrenheit, we don't have to derate that motor all the way up to that 4,000 meters or 13,123 feet. Let's do an example though to make this a little more clear. So in our example here, our drive is going to be operating at 6,600 feet or 2,000 meters, and if we would just derate off altitude, we'd have a 10% derate. And we're assuming though that 10% derate came from that drive is being allowed to operate at 40 degrees C, or in the ambient. If we know though that this drive's maximum ambient temperature is only going to be 30 degrees C, the maximum output capacity of that drive can be increased by 15%. So let's do some math. Our negative 10 plus 15% gives us a 0% derate. And nope, I did not do my math wrong, because remember, we cannot use this method to increase the output current on a drive higher than its nameplate. And this all circles back though to the UL testing that was done on that drive to get that product certified. So let's change it up and now talk about carrier or switching frequencies. The carrier frequency or switching frequency on a drive for an HVAC application may be raised to eliminate audible noises that the motor can make. And what we're talking about here is changing the rate at which the IGBTs fire on the drive. So what's the cause? Steel laminations in the motor can vibrate at a frequency audible to the human ear, which some people would consider annoying. Well, what we can do in this case is we can change this carrier frequency and increase it. But our concern now is that when we have a higher transistor switching frequencies, or the rate at which the IGBTs fire, it's going to create more heat inside the drive. So when we do this, the solution to this is that drive will now need to be derated when the carrier frequency on the drive needs to be increased above the default level. and as a result, the VFD will then have to be upsized to account possibly for the increased heat production. We'll take a look at our next example here, and what we're going to look at is something right outside the hardware manual. So I pulled this chart out of the hardware manual for the ACH 580, and this is for a 240 volt drive. And there aren't really a good rule of thumb when it comes to derating for carrier frequency, and that's because depending on the rate at which the carrier frequency is increased above default, it can change for each size drive, whether it be horsepower or even frame size. And it's not consistent. There's not a trend through the size increases. And it can change from even voltage to voltage. So when we look here, we're going to say our next example we're going to show this in is that we're going to take a drive that's normally rated at 4 kilohertz and change that switching frequency to 8 kilohertz. So in our example, we have a 10 horsepower, 240 volt rated drive that is a drive rating of 31 amps. We're going to connect that drive to a 10 horsepower motor that has an FLA of 24 amps. And in this application, this is actually going to require the drive to have a carrier frequency of 8 kilohertz. So if we remember from that derating table, the new derating value for this drive at 8 kilohertz is going to be a K factor of 0.86. We take that 0.86 and multiply it by the drive's nameplate output current rating. So 0.86 times 31 gives us 26.7 amps of maximum output current due to derate. We do our check and we see that we don't need to upsize our drive because 26.7 is greater than 24 amps. When we are talking about carrier frequency, there are some solutions though that are available in the drive that we might be able to avoid derating the drive altogether. The first one is carrier frequency foldback, and this is a software feature built right into the ACH 580. So what this foldback is that the drive will monitor the heatsink temperature of the drive and will automatically reduce the carrier frequency as the temperature increases on that heatsink to avoid overheating. Also, in the drive, there's a noise smoothing logic that's also built right into the drive. What this noise smoothing logic does, it provides a modular carrier frequency which varies the transistor switching rate slightly around a fixed frequency. This reduces the audible noise without having to increase the carrier frequency, which will then avoid a derating. Now, let's talk about input voltage and derating to a drive. A VFD can be powered off single-phase input voltage. This is more common in rural areas or older facilities. And when I'm talking about single-phase, we're talking about single-phase input power means that we only have 2 conductors instead of 3 that are connected to the input side of the drive. Right now, currently, we're only certified on 240 volt single-phase input on an ACH 580 that is serving 230 volt 3-phase motors. So here are our concerns when we're doing a single-phase input voltage. The input current to a single-phase drive will almost be twice that of the 3-phase input power. So the diode bridge will be seeing much higher currents than it was initially designed for. Next with our concerns are that the DC bus is going to have a higher ripple current upon it, which is going to create extra heating of the DC bus capacitors as they charge and discharge greater amounts compared to when they would normally have 3 phases of input power. The solution to these applications is that we're going to double the size of the VFD when we're inputting single-phase input voltage. We'll see this described in the next example. Let's take a look at this example. So in our example, we have a 10 horsepower motor that's rated at 230 volt 3-phase, and at a full load amps, that motor is rated at 27 amps. We're going to connect that motor to a drive that's being supplied single phase. So let's start by taking the amps of that motor and doubling them. So 27 times 2 is 54 amps. When we look at our standard ACH 580 rated at 20 horsepower, that drive is rated at 59 amps. So in this case, 59 amps is greater than 54 amps, so doubling the horsepower works. You can normally just double the horsepower like I mentioned on the previous slide, but I would always recommend verifying that the drive current is at least double of the motor current as well. One big note though, when you're doing this single phase input voltage to a drive, you got to take into account that the input wire sizing and input short circuit protection should be based off the drive size for single phase input, not just the motor size. Continuing with input voltage, I want to talk about supply transformers. And this is going to mainly apply to 6-pulse drives. So if we're supplying our 6-pulse drive from an open delta transformer, 3-phase voltage does exist, but the VFD will actually draw current as if it's coming from a single-phase power source. And this is due to the fact that on the supply side of that transformer, it has imbalanced impedance. When you are supplying a drive from a supply transformer that's an open delta, derate the drive as if the output current will be reduced by 50%. All right, everyone, pop quiz time. Let's put everything we learned here today to use. So here's our final example. In our example, we have a 25 horsepower fan operating at 230 volt 3-phase, and at full load, the motor on the fan is drawing 58 amps. This fan is located at an altitude of 6,000 feet. The drive that is running this fan is installed in an area that has an ambient temperature of 113 degrees Fahrenheit. Due to the location where this fan is, the job site is requiring that the drive have an output carrier frequency of 8 kilohertz due to noise. Here's the solution to our final example. So we'll first start by selecting a standard 25 horsepower drive that is rated at 75 amps. We're going to first do our altitude correction, and if we remembered, you do the altitude, so it's 6,000 feet minus 3,300, and we'll divide that number by 330, we get a D-rate value of 8% for altitude. Taking that 8% and timesing it by our 75 amps, we get 6 amps of D-rate due to altitude. Next, we'll do our temperature correction. So our ambient is 113, subtract that by 104, and divide that by 1.8, we get a temperature D-rate of 5%. Take that 5% times the 75 amps, and we get approximately 4 amps. Now, if you remember, we had the carrier frequency up to 8 kilohertz. So we have to go consult our hardware manual, and we'll see that the new K factor for this drive is 0.86. What we have to do is take that 0.86 and multiply it by the drive's amp rating. So we take 75 times 0.86, and we get 64 amps. This is now the new maximum output current that the drive can produce. So let's combine all our D rates. 64 as from our carrier frequency, subtract 6 amps from our altitude correction, and subtract the 4 amps from the temperature correction gets us a new maximum output of 54 amps due to D rate. We take that 54 and we'll compare it, and we'll see that compared to 58, 54 is less than. So this drive will not work for this application. What we have to do now is upsize to the next drive. The next size drive available is a 30 horsepower drive, and that drive is rated at 88 amps. So we'll go through it again. We'll do our altitude correction, which gives us an 8% D rate, and if we do our math, 8% of 88 is approximately 7 amps. Doing our temperature correction again, we'll get that 5%, and we'll take that 5% and multiply it by 88, and we'll get a D rate of 4 amps due to temperature. Next, we'll do our carrier frequency, and we'll notice that for a 30 horsepower drive, the K factor is 0.87. So again, it is important to check your manual. to see what the K factor is for each drive. So 0.87 times 88 gives us 77 amps, and that is our new maximum output that the drive can provide. So we'll combine all our D-rates. So we start with 77 amps. We'll subtract the 7 amps from the altitude correction, and then we'll also subtract the 4 amps from the temperature correction, which gives us a new maximum current output due to D-rate of being 66 amps. We do our check, and we see that 66 amps is greater than 58, so we know that the 30 horsepower drive will work in this application. Let's do a summary of what we learned here today. First, altitude. Once we go above 3,300 feet all the way up to 13,200 feet, a 1% reduction of the drive's output current and power occurs for every 330 feet increase in altitude. Temperature. Remember that for when you're operating, your operating ambient temperature is going to be between 104 degrees to 122 degrees Fahrenheit. You will need to derate the maximum output current of that drive by 1% for every 1.8 degrees Fahrenheit above that 104 degrees. And remember, this only applies to UL or NEMA type 1, 12, and 3R packages. Altitude and temperature. Remember that if the ambient temperature is below 104 degrees Fahrenheit, the D-rating can be reduced by 1.5% for every 1.8 degrees Fahrenheit reduction in temperature. And again, remember, we can't ever exceed the maximum output current rating of the drive's nameplate due to this analysis. When we talk about carrier and switching frequency, I would say always consult your manual. There's a lot of different ways that the D-rating can affect a drive because it varies so much between voltage, frame size, and horsepowers. So again, consult your manual. In wrapping up, we talked about single-phase input, and when we have this type of application, double the horsepower of the drive, but verify the drive's rating is also double of the FLA of the motor.